CS407, Numerical Analysis, Section 14.2, the Simplex Method. So, last time we looked at the general nature of linear programming problems and discussed first and second primal forms for linear programming problems. Today we're going to look at an algorithm known as the Simplex Method, and this is the principal algorithm used in solving linear programming problems. It was developed by George Dantzig in 1946 and provides a systemic way of examining the vertices of the feasible region of the problem to determine the optimal value of the objective function. Now, since you can have an entire course on linear programming, the text here, the Cheney text, only presents enough of the background information on this method so the reader can use it on available computer programs that incorporate it already, such as the solver that we saw for Excel. So let's take a look at the algorithm on page 599 to see if it's any help. And here is the algorithm as presented in our text for the Simplex Method. And you can see that the algorithm isn't going to be of very much help to us, especially if we want to learn how to use the Simplex Method. So instead of going into the details on this algorithm and what notation he's using, why don't we just go ahead and look at an example that illustrates how we would go through this. So consider again the numerical example from page 588 of the text. So here each unit of the first product requires 5 units of the first raw material and 3 of the second. Each unit of the second product requires 3 units of the first raw material and 6 of the second. We have 15 units of the first raw material and 18 units of the second raw material. Profits from the sales of the products are 2 units per the first product and 3 units for the second product. So our first step to get this solve this using the Simplex Method is to set up the information in a table. And a lot of times this is helpful because our linear programming problems are going to be set up as story problems. So if we can actually set up an information table with the items, the number of units that we're looking for each one, the amount of raw material that goes into each one, and the profit, this presents a nice summary of the problem so that we can work from there. Step 2, we want to write out the problem. So again, here we're attempting to maximize the function 2x plus 3y. Because we get 2 units of profit from the first plus 3 units of profit from the second, subject to the constraints that 5x plus 3y is less than 15, 3x plus 6y is less than or equal to 18, and we want both x and y to be greater than or equal to 0. In other words, we can't have negative amounts of products. So the next step is we want to rewrite those inequalities, less than or equal to 15 and less than or equal to 18, as equalities. And to do that, what we do is we insert something called a slack variable to change those to equalities. So instead of 5x plus 3y is less than or equal to 15, we have a slack variable, which is the leftover. And we say 5x plus 3y plus s is equal to 15. So say s was left over, we have 4y plus 3 leftover units of s, that would be equal to 15, assuming x was 0. Same thing for t. Instead of saying 3x plus 6y is less than or equal to 18, we can have t to take up the slack, so 3x plus 6y plus t is equal to 18, and we want to rewrite our objective function so that it's an equality. And we can do that by using the profit. So minus 2x minus 3y plus the profit is going to equal out as 0. That also makes this negative, which we're going to see is going to be helpful a little bit later on. Now we write the initial Tableau form. So here the initial Tableau form. We have x, y, stp, and a column for const. So once we write this out, we have 5x plus 3y plus s is less or is equal to 15, 3x plus 6y plus t is equal to 18, minus 2x minus 3y plus p is equal to 0. Now this gives us the initial feasible solution. X is equal to 0, y is equal to 0, s is 15, t is 18, and p is equal to 0. What this initial solution means is we don't manufacture anything, we don't make any profit, and we have 15 units of raw material 1 left over and 18 units of raw material 2 left over. While it's not a good solution, it is actually feasible. It is something we can do, is do nothing at all, and it is a feasible solution, but it is far from optimal. To make it more optimal, what we want to do is we want to select a pivot element. And we begin by selecting a pivot column. Now the pivot column is the column with the lowest negative number in the last row. And you can see the smallest negative number there is -3. So we're going to select that as our pivot column. Now what we do is we divide each constant by its corresponding element in the pivot column. So 15 would be divided by 3 and 18 would be divided by 6. So we get results of 5 and 3. And we're going to select the one with the smallest quotient, and that is 3. 3 is smaller than 5. So 6 actually becomes our pivot element, and we typically circle that when we're doing the simplex method. Next, what we do is we make the pivot element of 1. In this case, we basically divide everything in row 2 by 6. So 3 divided by 6 gives us 1/2. 6 divided by 6 is 1. 0 divided by 6 is still 0. 1 divided by 6 is 1/6. 0 divided by 6 is 0. And 18 divided by 6 is 3. Now what we do is we actually go about and do the pivot. And the pivot is like Gaussian elimination. We pivot based on the pivot element to make everything else in that pivot column equal to 0. So basically row 1, we take 3 times row 2 and subtract it from row 1. And we take row 3 and add 3 times row 2 to make everything else in the y column equal to 0. Now, since there's still a negative number down in the last row, we need to repeat steps 5 through 7. Okay, so you'll recall step 5 is selecting our pivot element. Well, -1/2 is the smallest negative number in this row. And so basically we get the lowest negative number in the last row, and we select that as our pivot column. So we're going to pivot on the column X, and then we need to determine which element in the pivot column we're going to pivot on. Basically, we do that by taking the constant and dividing it by the corresponding entry. So 6 divided by 7 over 2, and 3 divided by 1/2. We get 12/7 and 6, and certainly 12/7 is smaller than 6. So we select 7/2 as our pivot element. We take that 7/2 and turn it into 1. In this case, what we do is we multiply row 1 by 2/7. So x becomes 1. 0 times 2/7 is 0. 1 times 2/7 is 2/7. The -1/2 times 2/7 becomes -1/7. And 6 divided by 2/7 is 12/7. Then we pivot about the pivot element to make everything in the pivot column, the X column here, 0. And again, this is like our Gaussian elimination. So row 2 minus 1/2 of row 1 is going to give a 0 in that. And then row 3 plus 1/2 times row 1 gives us a 0 in that row. And we don't have, there's no negative number in the last row, so we're actually done. So we have a solution of x is equal to 12/7, y is equal to 15/7, and our total profit is 69/7, which if you looked last time, that's exactly what we had on the solution on page 589 of the text. So again, the simplex method looks about that feasible region and continues to attempt to optimize it at every point. And it does work pretty well. So let's take a look at a summary, and this is not from our text, but it's from Larson's Elementary Linear Algebra, Chapter 9, Section 3. So what we want to do is basically put it in standard form, one of the primal forms, convert each inequality in the set of constraints to an equation by adding the slack variables, create our initial simplex tableau, and then locate the most negative entry in the bottom row. This is going to be called the entering column. And then we select the row with the smallest ratio when we divide the corresponding column entry of that constant, and that's called the departing row. And a lot of times when you see the simplex method being illustrated, you have the entering variable and the departing variable, so that you can have some selections that way, and sometimes that's kept track of in the far left hand column. Using the row operations so that the pivot is 1 and all other entries in the entering column are 0. This is called the pivoting, and similar to Gaussian elimination again. If all the entries in the bottom row are 0 or positive, then we get the final tableau. If not, we go back and repeat those steps again. If you obtain the final tableau, then the linear programming problem has the maximum solution, which is given by the entry in the lower right hand corner of the tableau.